we are discussing about the recharge and discharge of groundwater. The main source of recharge normally to any groundwater body is through precipitation. The rate of percolation in different soil patterns may vary widely because that depends on the texture of the soil and the morphology of the terrain. The recharge could also be affected through streams when the water table of an aquifer is at a lower elevation than the stream level. This type of streams are known as influent streams, and we can see these kind of streams in arid regions of many parts of the world. And in the other hand, there are some streams that receive water from subsurface sources, and they are called as effluent streams. This type of streams are normally seen in humid regions of the world. Streams are normally seen in sometimes it can also happen that the effluent streams in the course of its run could also become influent at places. This depends upon the relative water level elevation of the stream and the groundwater body. We call this phenomenon as induced infiltration. There will be a direct recharge from the stream into the aquifer body, and the behavior of the aquifer outcropping directly in the bed of the river. The rise and fall of water levels in the stream are closely reflected in the observation of any kind of wells situated close by. The behavior of an alluvial aquifer when it receives recharge from precipitation, which indicates a close relationship between the rainfall and also a rise in the water level from the observation wells. Normally, the water level rises in the peak monsoon time and slightly later and start declining when it reaches to a minimum low level in the pre-monsoon period. So there will be one more situation in which the humid regions where water reaches the maximum saturation stage within the first few showers of the precipitation, and that does not take any more into its storage. This type of situation we call it as rejected recharge. Now, having seen all the general behavior of the alluvial aquifer and the factors that are controlling its movement, we will discuss about a few methods in the field that can help in the evaluation of hydrological parameters in an alluvial terrain. So, we'll discuss about a few methods. The evaluation of hydrological parameters starts with evaluating the flow parameters using a pump test. There are three types of test depending on the type of information we need. So, when it comes to the first test, we use these tests to understand the general behavior of an aquifer and also the well characteristics. The first test is step draw down test, or we can simply call as discharge variation method. And the second method is aquifer performance test or constant discharge method. So the first one is discharge variation method and the second is constant discharge method. Both the methods are of vital importance to a hydrogeologist. The first method helps in understanding the well characteristics and also the well losses, and the second method helps in evaluating the aquifer parameters, boundary conditions, and the spacing problems. The method in brief involving running a pumping test with known amount of discharge values and noting the drawdown lines or the drawdown values from time to time. The quantum of discharge and the length of the pumping test to be given depends upon the hydrological framework of an aquifer and the type of information we require. A number of time drawdown curves and recovery curves could be plotted and then analyzed to interfere the flow parameters, the boundary conditions, and also the well characteristics. So we go for the next groundwater occurrence in the hard rock. The occurrence of groundwater and the movement of the groundwater in hard rock regions such as igneous, metamorphic, and hard sediment regions is very complicated. In these recent years only, we have started exploring about the occurrence of movement in the hard rock areas. Hard rock regions comprise of granites, schist, basalt, quartzite, all those things. The occurrence or the movement and the distribution of the groundwater differ from rock type to rock type and also to its structure, the intensity of weathering, and the topographical variations. See, here you see the weathered zone, granite boulders, and the stream, the fractured rocks, the faults, the fresh basement, aquifer system, and the sediments, and the saturation zone. Joints, fractures, and other structural features are the most important for groundwater circulation. When you have a fracture or a joint, that will affect more of the groundwater circulation. The pattern of drainage, the long straight courses of river streams are the surface indicators for these structures. And the most common type of joints and fractures are nearly vertical and sometimes cross to each other at different angles. Most of the hard rocks are deeply weathered and they are covered with thick mantle of residual material. This will provide enough space for the groundwater storage and its development. See this red line on the top. So you can say that as a thick mantle and that is giving some space for the water to store and then percolate here. The weathered mantle is thickest in the lowlands and thinnest along the drained uplands and hilly slopes. So the major hydrological provinces we can see here when it comes to the particular location in the highlands you have the mantle thin because of the uplands and hilly and the places where you have weathered areas the same is thin. Okay, so we'll discuss about the groundwater in granite areas and also some related rocks. Granites, they are like the oldest rocks and they have a very stability. These granites give rise to variety of shades and they have different mineralogical compositions also. So the groundwater in granites are related to rock types occurring in the zones of weathering. The granite boulders are here and they keep on exposed to different kinds of weathering, erosion and all and they become to sediments and then the soil and then some of the layers gets the weather zone. So this is how the granites get fractures and they can become confined or semi-confined or unconfined aquifers also. So the groundwater occurrence, The depth to water table varies from terrain to terrain and also depends upon the hydrometeorological conditions, the thickness of the weather zone. Here you see the weather zone is thin little and here it is thick, here it is thin again. In general, in an underdeveloped area, the depth of water table will vary from 0.5 meter to 6 meters. That depends on the weather layer also. Groundwater occurrence and movement is controlled by the lineaments, the dolerite dikes, and also the quartz reefs in the granites or the related rocks. The lineaments in general contribute to the accumulation of groundwater, where dikes and quartz reefs obstruct the movement of the groundwater. The yield of a well in a granite depends upon the intensity and the spacing of the joints. So if you see here, we have some faults, and then we can take the example of joints also. The yield of the well in granite depend on the intensity and the spacing of the joints and also the weathering. In general, when the wells are dug or some bore wells are designed to obtain the maximum yield, sometimes even the tube wells could be designed depending on the potentiality of the area. The permeability or the transmitting characters are low in general for this group of rock aquifers. So after granite we have basalt. In the basaltic rock, the another important group of aquifers which can occupy quite a good amount of area in few parts of the world. Weathered basalt, fractured basalt, and vesicular basalts are normally the good recipients of groundwater. They can get more water. Groundwater occurs both under the unconfined and the confined situations. Vesicular and deep fracture zones normally give high discharge values. The vesicular regions of basalt sometimes are so potential that their yield characters could be compared to the sand and gravel aquifers of an alluvial region. And when it comes to the groundwater in sedimentary rocks, so in the sedimentary we have quartzite, we have shale, limestone, and some of the hard sedimentary that normally encountered. Apart from limestone, all the rest of the hard sedimentaries are rather poor aquifers. But sometimes the hydrological regime and the nearness of a recharge boundary could change the potentiality of the hard region also. The limestones are considered as potential because of the development of crastification. In general, many limestones are castified and hold good potential. The, the castified limestone are quite prominent in the Precambrian sedimentaries of India, and we can dig both the dug wells as well as bore wells also.